Alright, this is homework 4, part 4. We are going to write code to solve the varying temperature profile of the bar in part 2 using implicit Crank-Nicolson differentiation. Vary the time step empirically to show that there is no apparent stability links in the choice of dt. Alright, let's get started. So the first half of this video is going to be on paper, and the second half we're going to use Python. So the Crank-Nicolson implicit differentiation, basically what that means is that we are using future time step values as well as the current ones. So let's get right into it. This was our equation for solving the heat flow at the, basically up here, solving heat flow for a Cartesian coordinate system. And then the next part we did von Neumann verification that it in fact could only be 0.5, that the time step could only be 0.5 or else it was unstable. And now we're going to use the Crank-Nicolson method for implicit differentiation instead of explicit differentiation. So let's get right on into it. I already wrote out the left side of the formula here, so let's continue that. So we already know that we have this. We have j plus 1n plus 1 minus 2 plus 2t jn plus t j minus 1 n all over dx squared. But now we are going to have j plus 1 n plus 1 plus 2 t j n plus 1 plus t j minus 1 n plus 1 all over dx squared as well. So if you'll notice, before our r value was theta dt over dx squared, but now we add these together. We have theta dt dx squared times 2. So this new value we are going to call u for this implicit differentiation. And we can rewrite that as u tj plus 1 n plus 1 plus 1 plus 2 u j n plus 1 plus u t j minus 1 n plus 1. I think these are negatives actually. It could be incorrect, but I'm pretty sure these are negatives. Equal to, and then we have u t j plus 1 n plus 1 plus 2 u t j 1 plus u t j n. Now, in order to solve this system of equations, we have two known values, which are the front of the bar and the end of the bar. We know those temperatures, but we don't know all of the temperatures on the inside of the bar. So we are going to need to do a matrix multiplication. Where our n is n minus 2 because we have two unknowns. And and we will be seeing a very interesting matrix multiplication. So if we look at this matrix, here let me also specify that this is the right hand side of the equation. Left hand side. If we look at this matrix multiplication, and I won't try to explain this because it'll take too long and I'll probably screw it up 20 times. But when we go to multiply this, in the first column on the second row, we are going to get negative u. On the second column on the first row, we are going to get 1 plus 2u, and then minus u. But as you continue the matrix multiplication, you'll see a pattern start to emerge. Where this repeats in a diagonal pattern. And it just keeps going down the line and down the line. This is a very specific type of matrix. I want to say it's a triangular. It's not a triangular. It's a what's the name of it? Let me find the name of it real quick. It's blowing my mind right now. Be right back. So this type of matrix is a tridiagonal matrix. And when we multiply out this matrix, another pattern will emerge. Minus ut1. The next term will be see a pattern? One more. Definitely a pattern. So it's t to the n plus 1 minus tu, t to the n minus 1, and then 1 minus t to the n minus 2. So if we write that for the n minus 1 term here, we get t to the u to the t minus n plus 1 minus 2u to t to the n minus 1 minus u to the n minus 2. And for the first one, we would get u t to 2 plus 1 minus 2u to t to the first minus u to 0. Now, these, the first and the last, are unique in and of themselves because this t to the 0 term would be the right side of the bar, and the t to the left, t to the n would be the left side of the bar, or the opposite around. It'd be t0 is the left side, t to the right is the t to the n is the right side. Anyway, both of those values are knowns, and we can't have those in this matrix. So in order to get those to be unknowns, we're going to multiply those by 2, and that will allow us to continue doing this matrix multiplication. And this pattern here will repeat all the way up until the end of the matrix. So we'll just put that there, da-da-da-da. So that is the matrix multiplication that we are going to use, and we are going to code that up in Python. But that, so far, is the Craig-Nelson implicit differentiation method, and this will allow us to use any time step and obtain a stable graph. Like before using explicit differentiation, if we use anything other than 1/2, it wouldn't be unstable. But this method will allow us to use any time step and still have a stable graph. I will catch you in the next part when we use Python. Thank you. All right, homework 4, part 4, part 2, part 4, part 2, part 4. So we're going to code this up now. So you just saw me derive this implicit differentiation with our tridiagonal matrix. Now we're going to throw this into some code. I basically just copy and pasted from the last step, but this time we're going to use our implicit differentiation. I also changed R to U, and U is basically just R divided by 2. So let's put this in. So A is going to be our tridiagonal matrix here. So we're going to start with note the zeros. We have 3 diagonals, and they go from n minus 2. Let's put in our, so we have 1a that is negative, so one diagonal that's negative u. Another diagonal that is, what was our other diagonal? It was 1 plus 2 times u. So 1 plus 2 times u. And a third diagonal that was again negative u. Now, how were these in the matrix? So this is the first diagonal, so that's 0. But then they were in the matrix. If you look at this, this is starting u starting on the second column and is going all the way through. So that is going to be starting at 1 to the end. That's what that means right there. And this one is from all of them, so we can, that's diagonal 2, and that's all of them. And then the third diagonal here is from the all is the second, so that's the third diagonal, and that is from the all of the start until 1 minus the end. So that's what that is right there. And let's just line these all up here, make it look nice and pretty. Boom, perfect. Now for our for loop here, we need to plug in the right side of our equation here. So b is going to be equal to, basically we have to plug in these. So this is going to be u times t, but this t is, that's just n, so that should just be all of it, if I do recall. I could be wrong though. That is plus 1 minus 2 times u. Way too many parentheses. No, I don't. Do I? And that is times t, but this is going to be from n minus 1. So would that be 1 to -1? I think so. I think this is just 1 on. Okay, I think this is 0. We're gonna check this because I always get my mind blown when it comes to matrices. So we're gonna have to check that. And then can we also put that? All right, there we go. Perfect. And then that's minus u times t to the negative of n minus 2. Right. I think this is 0 because it's just n, so I think it's just 0. And then this is n minus 1, and then that's just n minus 2. So this just be -1, or is that? No, I think that's good. Like I said, I'm going to check it in a second. But then we also need to do the starting and the end values, so 0, -1. So when b is equal to 0, that's going to be b is equal to 0. Is that time? That's plus. It's going to be u times t 0. And then just do the same thing again, but for the end. Why I'm doing this right now is because of these two special cases at the start and the end, pretty much. Oh. U times t. Alright, very good. Now I'm going to check to see if these matrices are right, these indexes are right. I could be, because these always mess me up, so I could be wrong. I'll be right back. Alright, so this one was wrong. I had the right idea, but it's just 2. And then I have to throw a 0 in here for n minus 2. And then these are all good. And then the last thing we need to do is pull out our solver here. So that's for t in our range -1 is equal to, no, I always do that. Stop that. Thank you. We're going to use our banded solver. And as you see, if you can see, I already added it in here. That's just so we can solve our tridiagonal matrix. So let's see if that works. Oh. It did not work. We have an error. Ooh. Where did I mess up? Alright, I figured out my problem. I made an error in the last part of the homework, and let's fix that right now, actually. These are all supposed to be pluses. So that's where the error was there. That's why it didn't work when I tried to press go. So let's go back. Let's fix that. This is supposed to be a plus sign. And would you look at that? We have a nice stable graph at 0.5. Now let's change that to 1 second time step. And it's still stable. Alright, let's go crazy. Let's go all the way up to 2 time steps. So the thing is, as you go to more and more time step, it's not going to be more and more exact. It's going to be a little bit more linear and not as deviated because your time steps are so much bigger. But that's absolutely beautiful and very neat. We can have any time step we want, and we'll still have a nice linear graph. So that is the implicit differentiation. That is the Craig-Nicholson. And one more time, let's just run through. We had a triangular matrix. We inserted our diagonals and where they started, where they ended. Then we put in our matrix multiplication and our start and our end. We had to append those because they're different from the rest of them. And then we used the banded solver for the matrix to solve. And then just everything else we already did. And there is our graph. It looks fantastic. And then in the next part, we are going to, what are we going to do the next part? We are going to perform a von Neumann stability analysis for the Craig-Nicholson method using part 4 to prove that there is indeed no constraints. So we'll get right on that. I will see you in the next part, hopefully tonight.